Live. We're live. And we're doing algorithm problems. Coding problems, right? And today we picked a hard level problem from LeetCode. Why hard level? Because it's a good experience to try the hard level. And because we have already solved it in the past. So it's gonna be a practice of re-implementing on the idea that I think I remember. So I also sneaked out. Yes, like took a quick look at the code that that was accepted, and I will try to. I just wanted to check if that's the idea, and I will try to re-implement it. Let me restart the counter today. Let's see how much time it takes, because implementing is also a good skill, even when you know the solution. So this problem is called trapping rainwater given n non-negative integers representing an elevation map where the width of each bar is 1. Compute how much water it can trap after raining. Okay, so there will be water levels between each of these posts, and that's the shape of this landscape can hold the water. So we have height, these, we can also have zeros. And so this is one piece of volume. This is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Okay, so I have 6. Height n is up to at least 1, but up to 10 to 4 multiplied by 2. And the heights are 10 to 5, up to 10 to 5. The heights. Okay, the problem says that the topics are 2 pointers, array, 2 pointers, dynamic programming, stack, and monatomic stack. So I'd say there could be a solution using those, but the solution that I know is actually quite simple in its logic. So if we just try to traverse this list of heights, if we see this height 1, the problem is we don't know. The height 1 can only hold up to 1, but we don't know what is at the what is the height of some post down the line. Is it actually 1, or maybe it's just 0? So we could count these, like the maximum is 1, okay, but then if we have 0, we just delete the 1, delete that layer basically. Or let's say we go at 2, we'll go, and then we'll hit a 1, and the 1 was the highest. And so that means instead of collecting these three pieces, we can only collect that one. But I mean, how can you remove these three? There could be, well, they're all height 1, we know, and their length of 3. So yeah, you kind of can do that, but I mean, there's probably some stack solutions, that use these wonderful techniques. But the one that I think I have implemented was this. So imagine, let me close the door. When we traverse, we see that I mean, it's pretty easy, yeah. So we know the height of this current one, this post, but we don't know how high is the possible post on the other end of I mean, we don't, not only just the end, but all along that length of what's the landscape going forward? And if there is a higher post somewhere, then we can collect, it will store all the water that this one holds. So the trick is to find, I mean, if we know that wall, there is this, I don't know, infinite wall, or at least wall that's higher than everything else, then we can just go from, we can know. Then we'll know that, like, from this 2, that's the maximum it can hold. We collect all this difference, we count all the difference, but we know there is a higher post there, or at least as high as 2. If they're both like max length. And it doesn't really matter which, if we have several max lengths, it doesn't matter, because we know that we can count on the other end, it will hold the water. Now, all we need to do is we need to imagine. So we have this segment until that highest wall. We now need just to break down this entire landscape into just 2 segments, one before that wall and one after that wall, and just do 2 runs, and it becomes a linear solution. By the way, if we were thinking about a brute force solution, which we could do brute force, right? So is there like a brute force solution here? Yeah, we'll start from 1. 1 can hold maximum 1. Start from 1 and we'll go to the next wall that is at least of the height 1. So we'll find that wall, and then we'll count. We'll go again and count the water in it. And we'll compare these 2. I mean, we'll find actually, by the way, No, we cannot do that. We need to go all the way to the end and make sure and find the maximum length, right? Actually, I mean, I can't even immediately figure out the brute force. I mean, yeah, if we do find a higher wall down the road, that means this wall, that means that's how much we can store. I mean, we know the shorter one is the level we can hold, yeah. So I guess, yeah. Yeah, so then we'll go from that one. The problem is if there is no higher wall or same level, if there is only shorter wall, then we need to find the highest wall. I don't know, it's a little bit, it gets tangled in my mind. I get tangled. Yeah, the easy way is just to find the this highest max h. Max h is 0, and we're gonna go over the array for v range height. We're gonna max h is max h and b. So that is our what? That is our max height. And by the way, we need to find its index also. So max index is 0. So that means, what's with my indentation? That means we wanna save, because we need not that much the height. We need that index. The height will be, well, we do need to remember the height as well, yeah. So if, yeah, basically if max h is smaller than b, that means that's when we need to remember, yeah. We'll need to max h is v, max I is I, yeah, like that. Now we know which wall is the highest, and or one of the highest ones, the first of the highest ones, because yeah, we only update it when we see something bigger, but that's fine. Now, yeah, the volume. Or water trapped water is going to be start with 0. And we're going to go over these segments before the height, but we'll start with the left, yeah, and going towards that height. So we're gonna go for pointer array. Oh, so it's gonna start with 0 less than max I plus plus. Yeah, so I'm gonna have that pointer. And we need to track this current max. So if trap I, can we call it just water? It's water. So trap I, if current max is smaller than this trap I, then we update current max, right? Is there anything else we need to do? Yeah, we need to update it. I mean, otherwise, all we do is well, that means we start new. Otherwise, all we do is we have this trap I. That's our current depth. And we have our current max. And we minus trap I is the volume that we can add. But yeah, if they're equal, we add nothing. Yeah, we say water plus this thing. Yeah, this volume. Yeah, that's how much water it holds. If it's negative, we don't want to. Yeah, so, but if we have a situation when the wall is higher than the previous, yeah. So this happens only, yeah, then we update current. Yeah, if when it's updated, there is no water to collect, so we don't need to collect water. We just say that current max is trap ith. That's kind of it. I mean, we'll collect. So now we count that water. Then we'll go do the same thing from the other end, right? So we see if it's bigger, there's nothing to collect. If it's not bigger, if it's smaller, we look, yeah, the maximum is 2, where the trap is 1. Yeah, so maximum is 2, trap is 1. Oh, yeah. Height is 1. Yeah, we collect 1. Pretty clear. Next, we need to start again current max. Should we write a separate function? Because we're going to be repeating, I mean, the logic, obviously. But it's just going to start from this direction, then from that direction. Can we write a function that can do that? It will run a... but, I mean, the direction is going to change. Yeah, it's just easier to do it. For now, I will start at length of trap -1, which is the last index. I will be until I is higher than max I minus y. So now this pointer does that. But the rest is probably the same. We collect water when it's higher, we update the current max. And we need to return water. Let's see if it works or if we have missed something. Wait a minute. If current max is smaller than trap, I'm trying to understand what is its problem. I is an index. Oh, yeah. Trap height, yeah, instead of well, only this one. No new variable, yeah. Yeah, look at that. Now this is a yeah. So we solved it and accepted. Let's compare. We have this in our editor. Let's look at the previous one. And let's compare the code. Looks exactly the same, right? Yeah, naming is a bit different, but the rest is exactly the same. Yeah, so that's the solution to this. One of the solutions, I mean, what is another? Oh, monotonic decreasing stack. What is that? Ooh. Nested loops. All right. Well, so obviously there is more solutions than that. But this one is probably the easiest one. And the trick was to just think about it. I mean, we're just missing, one highest wall. And because we can split the this full landscape into segments. So we just did it on that side of the wall and then this side of the wall. Yeah, and it was pretty straightforward. I don't know if we can do a function that count. Let's just do a function that will go like But you see that if we pass two pointers, it needs to go either in this direction or in that direction. So it's not just the pointers, these pointers change, but also this operation changes. I mean, we can express it a bit differently. And also pass that. Yeah, but it's just easier to do it without this extra function. Yeah, so I think it's a good good exercise, and an example of pretty good solution for a problem that's otherwise just not easy to wrap your head around. It's hard level. First 50. So that's our problem for today. If you like this solution and this video, feel free to like and subscribe. And otherwise, thank you for watching, and we'll see you in the next video.